Hello and welcome back to the TFK Deep Learning series, episode 2.3. In this episode, we are going to see how we can implement simple and multivariable linear regression in Keras. But before that, let's have a recap of the previous episode. So, in the previous episode, we implemented the simple and multiple linear regression in TensorFlow. So, the example which we took was predicting the profit for a food truck given the population. So, for simple linear regression, there was just one input feature for X, and for multiple linear regression, there are two features for each input. So we are, in this case, we are predicting the house price given the house size and the number of bedrooms. So the target was for simple linear regression. Given this sort of data, we need to learn a linear regression model. So it will be a line it will be a line which after trained will be the best fit line for this data. And for multiple linear regression, this is visualization in 3D. So given this multi-dimensional data, it had to learn one hyperplane which is the best fit for this data, such that it can predict a new output after training. So this is one overview picture of the multiple linear regression, and I've explained this in episode 2.1, how given the features, how we can, weight it, and then we can compute the output, then we compute the cost, and then we update the weights based on gradient descent algorithm. So you can go and have a look at episode 2.1. So in this episode, we are going to implement simple linear regression in Keras, multivariable linear regression in Keras. Then we'll also see how we can use tensorboard with Keras to visualize the training and to visualize the model graph. And we'll see that in Keras how we can save the model graph, our model, as an image file. And then uh, we'll also see how we can save the final train Keras model and that load it anywhere we want to deploy it. So the example which we are going to use is same as that we use in previous episode for TensorFlow, and the target will also be same, that given this sort of data for simple linear regression, we have to learn the best fit line, and given you know this sort of data, we have to learn a hyperplane which will be best fit to this data. So this is just to show you one comparison. So this is in TensorFlow and this is in Keras. So in TensorFlow, if you want to implement a linear regression, you have to define placeholders for your input and output since it's a supervised learning. Then you have to define variables for your parameters. You have to define your model. You have to define loss function, optimizer, and finally we launch the model in a session and train it. So in Keras, it just reduces to just 3 or 4 lines of code. We simply define a sequential model, and then if you want to add any number of neurons, or as we move from input to output, the different number of layers, we can simply do it using model.add. And in case of linear regression, we have just one layer, and then we compile it using what loss function, error function we want to use, and the optimizer we want to use, and then we finally train it using model.fit. So you just see in Keras, everything gets really simpler and easy. So I think enough of talk. Let's code out this model, simple and multiple linear regression model in Keras. And this is a Jupyter notebook for implementation of simple linear regression. So the problem is to predict profits for a food truck in a city. So let's load the modules that needed for this code. And let me also print the version of TensorFlow and Keras I'm using. So I'm using the TensorFlow version of 1.4.0 and Keras version of 2.0.4. Now let's load the data, and you can see this is the first 5 samples of data. This is the population and this is the profit. So this example is taken from Andrew NG Machine Learning Coursera course, and you can do a data.describe to get an overview of the data and the number of samples, the 97, and you can then split the data in data X as the input, which is the population, and data Y as the output, which is the profit. And then we can do a scatter plot of the data, how our data looks like, how scattered it is, and we can do a simple plot with matplotlib also. And you can just see the shape of each data sample. So this is the shape of input data, that is X, it's 1, and shape of output also it's 1. and you can see the first 5 examples like this. So once you have loaded the data, now you have to define and train the linear regression model, which is A equal to W into X plus B. And again, if you are not familiar with the theory of what linear regression is, or then I like encourage you to go and watch episode 2.1, where I explain in very detail the linear regression model, and I am implementing this based on that explanation. So now we can create a linear regression model using two way. One is through sequential model. So you just call the sequential class and you define this model, and then you add over it. So how many input units you want to add. So let me just go to this diagram. So if you see, this is the input, and over this we'll be adding this layer which has just one unit of node. Okay, so that's what it means by this line. Where is it? Yeah, so model dot add dense 1, and the input dimension which was coming to this unit is 1, because input is x dimensional. In case of multiple linear regression, this input dimension will become 2. And as you know from theory that we give a random initial weight, so this is a default provided by the Keras. So you can go and look at Keras documentation, and there are number of initializers of how you can initialize the weights, and the activation is linear. So when we see in logistic regression and neural network, this activation function may be sigmoid or ReLU and all that. So linear means it will output the same thing. So if you know the theory of, again, the linear regression, so this A will be W into X plus this B. So this will be this A, and linear means there will be no changes. A will be output as A itself. Okay. And as I said, it's a dense means this unit is connected to every input, every node of the previous layer. So in this case it's just one, so there's just one connection. But you'll see in future what to say future tutorials, in case of neural networks, when there are more than one, even in multiple linear regression, so this will be connected to every other node in the input. Okay, so let's not deal much with the theory. Let's just see how we can implement the simple linear regression. So once you have done this adding, you can compile the model, which loss function you want to use and the optimizer you want to use. So matrix, what you want to monitor. So it is same as the loss function, it's mean square error. And in while discussing the theory, I explained with the gradient descent. But here, I'm just giving RMS prop, which is a better optimizer. And this the concept of weight updation remains same as in gradient descent, but there are the way we update the weights, and the way the learning rate is defined is different in this case, and this works better. So you can try with SGD and anything and just experiment it out. So we just compile this model, and you can use model.summary to have a look at it of what are the layers. So we have just added dense layer, which is just one unit, and it has two parameters, W and B. So this is total parameters, and these both are trainable. And you can use Keras visualize utils to visualize the same model in graph form. So this was the input layer, its name was input layer. So input layer, it was one unit, and the output, it was just one, the input node, is just this one. So it's just one unit, and either it's one unit in the input form, nothing is coming, and output also just one thing is going out. And we'll see in the multivariable linear regression it will be 2. And the dense layer, that the next layer, so which has one input coming and output it was going just one. Okay, so another way to create linear regression or any model in Keras is through functional API. Okay, so functional API is more useful um, when we're dealing with multimodal networks. So it treat every layer as tenses. So first we define inputs. So we give input which shape is 1, and then we add a layer over it. So it's a dense layer which is having just one unit. Its activation is linear, and it is connected to the previous layer, which is the inputs. So we just give it here. Okay, so these two are the layers, and then we define our model using functional API model, where input is this inputs and output is the predictions. And then you can compile same using any of the optimizer. I'm using Adam. You can give the loss, you can give the metric, and you can similarly see the summary. So the input was having no parameters because it's just the input x, and the output a, which is equal to w into x plus b, it is having two parameters. And similarly you can visualize this graph also, it will be similar. Okay, and now let me delete the previous if I have any. So let me delete this log. So now you, through this command we call the tensorboard, and this tensorboard is provided by TensorFlow, and since this Keras is a backend of TensorFlow, we can use this tensorboard. We can give the log directory where to store the logs, and then finally we train our model. So we can vary the batch size, how many batch we want to feed in at once during the training, during the weight up, like for every weight updation. And you can use this argument for shuffling the data or not. So if you shuffle it, it trains better in case of various problems. So you can try it out depending on your problem. And we can use these callbacks to use the functions that will be fed into the training, and during the training we can get information. So we'll see later that we can also do a model checkpoint to save intermediate models. For now, let's just go with the tensorboard callback. So it starts training, and you can see the mean square error reducing from 47, 41, 36, 15, 14, and I'm just training it for 100 iterations. So let's see. And okay, so yeah, so it is trained and we got a mean square error of 11.1452. It can do better if we optimize the model. So I'm just showing how you can, define and train your model. Not, I'm just not optimizing this problem, so you can try it for your problem. And since we use a hist here, so the hist variable stores the loss and the accuracy. So in this case we are just doing a training loss, we don't have any accuracy nor we have validation loss. So in case of classification problem, or even in the next logistic regression episode, I will show you that while training you can feed the validation data. So while training it will train on trained data, and after every iteration it will even evaluate on the validation data. So in this problem we don't have enough data, so let's just see this, and you can see this training loss. So it's reducing from around 60 to going around 11 for 100 iterations. So we can see that our model is learning, it's improving since the loss is reducing. And the same thing you can visualize in tensorboard. So we'll launch the tensorboard a little later. So now you can evaluate the so once your model has been trained, you can evaluate in any different data which is not used for training. So in this case we don't have a separate test data, so I'm just taking 20 samples of the training data as test data and I'm evaluating it. So you can see that test score as uh, you know 21, and this is just one metric. This is the mean square error. In case of when we are doing classification, we also measure the accuracy. So we'll get two values, one will be for the loss and one will be for the accuracy, but in this problem we are just measuring what to say, a loss, which was the mean square error. If you remember from here, where is my model? So this is the loss, which is the mean square error, and the metric, which is also the mean square error. So okay, so that's why this where is it? Yeah, so so these two values are what we give in the during the training. So this is the loss and this is the metric, which in this case both are mean square error, and this I did for 20 samples. So if you and just to show you, like in real time this data will be different, the test data will be different. Suppose if you just do for entire training set, and you see, so let's see what it should be, something around, so you see it's 11 11. This was our final, from the graph you can see it was something around 11, so that's what it is. Okay, so forget about it. Okay, so not don't forget about it. So you should remember, in order to like check how your model is doing on test data finally after training. And then given, like once you have trained, you can also uh, given a new test sample, you need to predict what will be the output. So you can do that using this model.predict. So I'm just taking one sample, so this will be one, suppose assume this is the one test sample, new sample, and then we need to predict using this model. So let's just predict, and compare it with the true value. So in this case, I knew the true value because I'm using the training data, but in case of your problem, you may not be knowing the true value. So in this case, the model is not good because you see the predicted value and the true value are not very close. So I just wanted to show you the functionality which you can use, and you need to like further optimize it, have more data to train better model. Okay, now so this, if you want to do a prediction over the entire test data, then just feed x test and it will do a prediction of entire test data, and this I will use for generating the final graph, or sorry, yeah, the model. So, and also you can get the trained parameters. So if you want to use the trained parameters, you can get it using model dot layers. So in this case, we know we are having uh, in case of a deep neural network, we'll have number of layers, so you can specify the layer numbers using this. And let's see, so in our case we're having just one layer, so we added just one dense layer, if you remember, and it has two values. A, if you remember, the model is a equal to w into x plus b. So this is w, your weight, and this is the bias b. Okay, so it is generally the weights will be number of, there will be many number of weights. So in order to get the weights, we'll use this, and for getting bias, we'll use this. So this is the final trained parameters, and this is the y test predict using model.predict. And this, similarly, you can predict it using what to say, this trained final value of w and b. So y test predicted 2, if you say, it will be x test into w plus b, because that's what the linear regression model is. If you remember, a equal to wx plus b, and the after training we get the final value of w and b, and we can compute this predicted value using this formula also, in case of yeah, this one. Okay, and this we can visualize it because there are like very only two parameters, but if you train bigger model, there'll be more number of parameters. So it's better we just do this model dot predict rather than doing the computation ourselves. Okay, so for linear regression we can do it just simple equation. So now let's plot the model. So in x we'll have data, and in the y I am having y test predicted. Okay, so this one. Okay, and let's plot this. Where is it? I run this code, yeah. So you can see this is the model and this is the data, and similarly you can also do your own y test predicted with the final w and b value. It will come similar. So this is the similar thing. Okay, so I'll just change it to 2 only. Fine. And now yeah, this is to do a scatter plot, same thing. It's no big deal. Okay, now you can, once the model is trained, you can save this model and take it out of your training environment and deploy it anywhere. So how you can save the model is very simple in Keras. Model.save simple linear regression model.h5. So it will save the model. Now suppose, imagine you want to load it somewhere else. How you can load it? So you need to call this from keras.model import load model, and then you have to use this and give the model file name, which in this case is this, and then in order to confirm that our loaded model is the same, I will just print the weights and compare it with the trained final weights which we achieved. So you see, this is the weights I got from the loaded model, which is 0.802 and minus 0.68. And if you see here, 0.802 and minus 0.689. So you can confirm that by this. You're saving the model and you can load this anywhere, and then you can again do the test by using any given any test data. Y will be x into this w plus this b, and we can get the output. Okay, and finally you can save this graph which I showed you here, this one, as an image file using this function or using this block of code. So it will save it and you can see it here. So it was simple linear regression model.png. So this is your graph. Okay, so yeah, now one thing is just left here is launching the tensorboard and seeing this loss function. So let's launch the tensorboard, and we can, whatever we saved in this directory, where is it? Yeah, this directory, we can run the launch, what to say, the tensorboard through this directory and visualize it. So let's do that. So I have opened the Anaconda prompt and I have activated my environment where I'm working. And now in order to launch the tensorboard, we just type tensorboard minus minus log directory, and we give the directory where our event files are. So in my case, it's in this folder, and I will give it here. Okay, and I'll just enter. And you can also specify the port number by just doing minus minus port. Okay, so it says that it's in 6006. If and you can do explicitly also by mentioning. So let's just give a local host. So localhost 6006, and let's see my tensorboard. Okay, okay. So maybe I know the issue here. It's not able to find the event file. I need to enter the D folder. I don't know, somehow from C it's not able to go to D. I don't know the issue, but it works like this for me. And yeah, so it's there. Now let me refresh this. So you can see we had two metrics. So one is the loss, which was the mean square error, and another we specify metric as mean square error. So this is this one. And if you have any other metric, you can specify here. So it will plot whatever you give during the training, loss, and whatever metric you give. In this case, I gave same the both. Okay. And this is the graph, TensorFlow graph. If you have used TensorFlow, you'll know it. So in this way, and you can activate other functionalities. But this is the way like you can call tensorboard in Keras by calling it through callback and putting it inside a model.fit. So that's all for simple linear regression. I hope you got some idea. And let me go to multiple linear regression, and let me clear all the output. So in the multiple linear regression, as I told, now there are for input, the input has having two features, and there is one output. So if you consider from layer point of view, so we have just one layer which is getting this input. It has three parameters, w1, w2, and a b. Okay, so the problem is to predict the price of a house given the size and number of bedrooms. So let's load all the modules that we need, and let me again print TensorFlow version and all that I'm using. Let me load the data. So now the data is size is this, bedroom, and price. Now you can do a data.describe, and you can get description about data. And now let me do a 3D plot to have a visual of our data. So this is how our data looks like: size, bedroom, and price. Now if you see in this case, the bedroom is in units like 3, 2, 4, and the size is 2000, and the price is 39, or what to say, 3,99,000. So it's like not all the features, if you see, they are kind of different. The scale is different, and it's not good for training. So we go for feature normalization. So it adjusts the scale of the feature, and one way is doing zero mean and unit standard deviation. So you can do this simply using this mean and standard deviation. So now you see they all come in the range of 0 to 1 kind of range. Okay, if you see, so we just do a doing a subtraction. We subtracted it from the mean, and then divided it by the standard deviation, and then you can have a description of this. So when your features, you see the scales are very different, it's a good practice to normalize it, so it helps the network to train better. So now our feature name is size and bedroom, and we will have our data x as this two inputs and data y as one value, unlike in the previous case where data x was just population, data y was profit. In this case, for data x we have two values, so it's a multivariable linear regression. And if you see, you can see the input shape is now 47 by 2. So there are 47 samples, and for each samples there are two features. Output shape is 47, and this is not single input shape, it should be data x1. I don't know why I printed this out. Okay, it should be number of samples, I guess. Yeah. it should be number of samples. So I guess it should be something like this. Okay, so now we convert this in array, and then we plot. This is the plot of normalized data. It will look something similar. And after we're done with data, so our data should be in this format. It should be in array format and all this shapes. Now we go for defining our linear regression model, so which is w1 into x1 plus w2 into x2 plus b. Again, if you are confused with the theory, go and watch episode 2.1 to have a clearer concept on this. And similar to the simple linear regression, we can do it in two way. So we can create a linear regression with uh, what is a sequential model, or we can use functional API. So in this case, if you remember, as I told you, so we are adding one layer which is having just one unit, but its input dimension is two. So you see here we are adding this node which is one unit, but it's having an input of dimension two, unlike the simple linear regression where it was just one. Okay, and we are giving again the loss as mean square error, optimizer as Adam. And if you want to give any metric here, you can give metric as mean square error. And if you don't want, no need, so because both are same here, loss and the metric, but in case if you have some other metric. And another way is using functional API. So input shape, now instead of one there are two features, and then we are adding one unit over it, this a unit. And then activation is linear and it's getting the input from this. And then we define the model using functional API mod, capital M model, which inputs is this and the output is prediction. And then we compile, same, giving optimizer whatever we want, and the metric. So you can look at model.summary. So now we'll have three parameters. So this is, so we have just one layer which we're adding to the input, which is the dense layer. It has just one unit, but it has three parameters, w1, w2 and b. So there are total three parameters, and all these three parameters are trainable. Okay, and you can display this using again this graph. So now you see the input features are two, and we are not like output, we are, the input features is two and we are outputting that two features from this. So it just means this is the input layer, it is two features and we are outputting this two. So this is just a way to representation, especially it make more sense when we have deeper networks. It's just not simple. Okay, and then for the dense layer, for the last unit, a unit, this a unit, it's having input of two and it's outputting just one unit. So that's what it means, it's having input of two and outputting one unit. So now let's train the model. So we'll call the tensorboard using tensorboard command. We'll give the log directory where the logs will be stored, and then we'll use a variable hist to then assign this training part. So instead of model, let's do a training with model 2. So instead of sequential model which we did earlier, let's do a model which we define using functional API. Let's do the training using this model. And yeah, so I'm giving batch size of 1 and iteration or number of epochs is 100. So let's do the training, and when we are doing the training, let's also visualize the tensorboard simultaneously. So let me call the tensorboard here, and let's see, or what happened. Okay, the training is complete. Okay, I should have gone here. So yeah, so let's see the tensorboard, and it will be again local host 60. Actually, what I wanted to show you is that you can see this training directly in tensorboard. So let me just do one thing. Let me close this. Okay, and let me delete this event file, and let me do the training again. So let me reinitialize this model 2. Okay, so in order to reinitialize, I have to put it in some another cell and let me run it. Okay, now let's do the training again here. Let me give 150 epochs. Okay, so it takes some time to do, and the meanwhile let me call this and let's see. So you can see like I don't know, again you missed it. Maybe I have to give it for 500 iterations, or it is, yeah. So you can see, so before it was 80, 100, now it go up to 120. So this is 140 and 150. So like what I wanted to show you was like if you have more iterations, then you can directly launch tensorboard and see how your graph is going down or not. Okay, so that was my aim. And okay, another way after training you can do is using this hist. So hist variable, so you can simply see the plot. It will be similar plot as we saw in the tensorboard. So once you have trained the model, you can again evaluate the model, and you can evaluate using new test data. But in my case, I'm not having any test data, so I'm just using this. And there were two metrics. One was by default loss, which is mean square error, and the matrix in this case also was mean square error. So both will be same. Or you can define any other metric if you want. And for new any new test data, you can again predict the output value using model2.predict. I'm using 5 values here. Given any sample, any single sample, you can predict it, and I'm comparing with the true value since I know it's true value. So just do a comparison. So it is similar to doing model.evaluate, but in this case you need not do comparison, because in real life when you get a test data, you will not know its output, and that's the goal, to predict the output of unknown test data. Okay, now one thing you should remember, since we normalize the data, if you want to get the actual output, you have to denormalize it. So what you have to do is, since we subtracted mean and divided it by standard deviation, so for the final output, you need to multiply standard deviation and add the mean. Okay. So now let's do a prediction of the entire test data, so we can plot our linear regression model. And again, you can get the trained parameters here using this. Okay, so in the previous case, we were using sequential model. It's giving blank. I know the reason, and I want to explain it here. So if you see model.summary, model is a sequential model. Here in the input is not considered as a layer. So directly the output unit was the layer. So when we give model.layer of 0, we got the output. But in case of functional model as API, everything is considered as a layer. So even the input was considered as a layer, and even the output dense unit was considered as a layer. Okay. So the zeroth layer has no parameters. It's just the input. So instead of 0, we need to give 1 here. So we'll just give 1. Okay, and the weight value, there are two, w1 w2, and this I explained in the previous episode, that matrix based approach. But again, it will be together like for each layer. So as the output is a equal to w1 into x1, w2 into x2 plus b. Okay, so you can get w and b separately here, w and b. And why I'm doing this, because I want to plot it. So if I define X a surface with a mesh grid of this range 100 values, then the output will be x1 into w of 0, which is w1, plus x2 into w2 plus b. So this is what our model is, and that's what I'm doing here. So if our where is yeah, it was w1 x1 plus w2 x2 plus b. So that's why I got the weight separately and I multiplied it just to show you, and also to plot this 3D plot. So now if you plot this 3D plot, you will get something like this. So this is our trained model, this hyperplane. So data x is not psi, it should be size, and I did some mistake somewhere. I don't know. Okay, no problem. And yeah, then again you can save this model as model2.save, and you can load this model anywhere, and in order to verify it, you can just check it with your w and b. So w is 0.88 minus 0.055, and that's what it is. And you can save the model This is the model weights file. You can save the model graph as PNG file, and you can see it somewhere here. Multiple linear regression. Yeah, this is your model file. So I hope I gave an overview of what are the Keras functionality that we can use to train and predict and save our Keras model. And like it may sound confusing at first, but once you start using it, it's really easy, especially for complex models. This all features are really comes in handy. So I guess uh, yeah, so I guess that's all from this episode, and I covered everything what I have discussed, and it was useful. So I hope it was useful, and tune into the next episode, because in next episode we'll be understanding the theoretical concept of logistic regression and gradient descent from neural network perspective. So mainly, my goal is to go in neural network direction. So we'll understand logistic regression from that perspective, and it will be really interesting. And yeah, tune in for the next episode. And till then, if you like the video, you can hit the like button, you can comment your question, you can subscribe. And if you find the video useful and you want to support me, you can support me on Patreon and PayPal. Until then, the links, all the links for this notebooks and everything will be given in the description. Until then, keep learning and keep exploring neurons. Bye.